Okay, I have something new to share with you today. Now this can double as an amazing card trick as well as a mathematical demonstration of the power of symmetry groups. Okay, so let's gather up our well-mixed deck here. Now I'm going to assume I have 4 spectators across from me here. And so what we need each of them to do, if I can not drop the cards here, we need each of them to choose 2 red and 2 black cards. And it can be any of those cards. So maybe spectator 1 way over here chooses, 2 red, sorry, going off the screen, 2 red, 2 black there. Let's see, spectator 2, maybe they grab these right here. Spectator 3, see, maybe that, and then maybe the queen. And then spectator 4, 2 red and 2 black right there. Okay, and it is a free choice. Okay, now you have each of them arrange their cards so that one color is right next to each other. So cards of the same color are right next to each other, but cards of the opposite color are not immediately adjacent to each other. Okay, so for example, let me just slide these over. Spectator 1 may go with this ordering right here. That's fine. We have the red together and the blacks are not next to each other. Let's see, spectator 2 might go like that. We have the black together, the reds are separated. Maybe spectator 3 goes with the same thing. 2 black are adjacent, but the reds are not. And then maybe spectator 4 goes with this organization, which is similar to spectator 1. Okay, so all of these structures satisfy the requirement that the cards of one color are adjacent to each other, and then the cards of the opposite color are not. Okay, and then you can just have them turn these down. Okay, so let's just talk about symmetry groups just for a moment here. So a symmetry group is a set of operations or actions that can be performed that doesn't change the fundamental nature of an object or whatever it is you're measuring on that object. Okay? So of course, what we're going to be doing with these packets are shuffles. Now shuffles are just permutations. And that's what makes up groups. Groups are sets of permutations, ways of rearranging things. So for spectator 1, what we're going to have them do is mix their cards as much as they would like using something called the left-right shuffle into 2 piles with random stacking. Now they can do this as many times as they like with the stacking decided by them. Okay, so you could actually just give them the cards and let them fly with their mixing. The second spectator, what they're going to do is even more amazing. They're going to deal out into 4 piles in this way. They can randomly stack the top row on the bottom or vice versa, like this, and then randomly stack the 2 halves. Alternatively, what they can do is randomly stack the columns on top of each other and then stack the resulting piles. So they could go column 2 on top of column 1 and then the top one on top of the bottom. Okay, so I have them mix their packet in that way while spectator 1 is mixing their packet with the left-right shuffle. Third spectator can do the Australian down under as many times. Let me do that more slowly. Down, under, down, under, down. Last one goes on top. They can do as many of those, if I can speak, they can do as many of those shuffles as they like while the others are mixing. And then spectator 4 is going to do something called a Charlier 1. And it's a top to bottom, bottom to top sort of shuffle. And I'll add a link in the description below to this kind of shuffle actually, if you haven't seen it before. So each one of them goes through and mixes their packet using their assigned shuffle as many times as they like. And once they're content with the mixing, you just point out to them that although they started with different packet structures, Some of them had a red, black, black, red, and the others had a black, red, red, black. And they mixed their packets differently and were in control of how many times they performed that mixing. There's something that remarkable remains despite all of those choices. And so what we're going to do to finish is we're going to have each of them go ahead and use the Klondike shuffle demonstrated here. You take the top and bottom off as one, and then that leaves you with a final pair, and then to just set down that pair. Spectator 2, they would take the top and bottom off, set down the kind of middle pair there. Spectator 3, top and bottom cards off as one, and then the middle cards on the right. Spectator 4, top and bottom cards off, and then the middle cards right there on the right as well. Okay, so I have a written prediction off to the side. So just think about it. What could I have possibly predicted that would be true for all of these? Okay, so let's just look at that first. Every pair will consist of cards of the same color, either both red or both black. Okay, now as a card trick, that should be incredibly surprising if it were true. Okay, we don't know if it's true here. But mathematically speaking, what it would tell us is that the four mixing procedures, which genuinely mix the cards differently, are all part of the same symmetry group. And that those operations leave these packet structures in some sense alone. They don't fundamentally destroy them. And then the Klondike shuffle, its role is to draw out any remaining structure that the packet may have that was not destroyed by these four very different shuffles. Okay, so this is where we'll discover whether or not our four shuffles are part of the same symmetry group for the two kinds of packet structures that we started with. Okay, so the claim is each of these will be pairs of the same color. Okay, well, we're doing okay so far. Okay, halfway. Yep, okay. And there we go. There as well. And the final one also. That is amazing. Okay, so that's an example, in fact, a very powerful example of symmetry groups in card magic, as well as a physical model demonstrating the abstract mathematical idea of a symmetry group. We can actually see it unfolding before our very eyes. Okay, so everything I've done here you can do right away. There's no sneaky sleight of hand or anything funny. And when I said that people can mix those individual packets performing their assigned shuffle as many times as they like, they truly, truly can. And in the description below, I'll give a more technical write-up of what's going on here that could actually be presented in a classroom setting to clarify this as a mathematical demonstration of the use of symmetry groups in card magic. So thank you for watching, and take a look at other videos on the Absolute Math Magic channel.